this video, we're going to be looking at forces and their interactions, and this is video number 1 of 6 for the forces topic. So let's get right into it. So scalar quantities have magnitude only. This means there is only a number associated, or an amount. There is not a direction associated with scalar quantities. Magnitude just means a measurement or a number. So scalar quantities have no direction, just a number. Vector quantities are scalar quantities, but with a direction as well. For example, 3 miles west. You can remember this with a character from Despicable Me, known as Vector, who repeatedly proclaims, "I have both magnitude and direction." You need to know about distance and displacement. Distance travelled is a scalar quantity and has only magnitude and not a direction. Displacement is a vector. You measure with numbers, like 3 miles, but you have travelled in a direction as well. In this case below, you have travelled south-east. So if we have a look at this example, the 97 bus route, the 97 goes from Newcastle to Metro Centre, and that is a displacement of about 2 miles. But the actual distance travelled is more like 6 miles because the bus doesn't go a direct route. So if you take the route 97 from Newcastle to the Metro Centre, your distance travelled may be 6 miles, but your displacement will only be 2 miles west. Representing scalars is easy. You just write down the magnitude and the units, like any other unit in physics. Representing vectors is slightly more complicated. You can use arrows to show the direction, and the length of the arrow shows magnitude. For example, 2 newtons of force, or 6 newtons of force to the right, could be represented like this, where here we'll have a 2 newton arrow, and here we have a 6 newton arrow, and as you can see, the 6 newton arrow is slightly bigger. So what has this got to do with anything? Well, the whole topic of forces has to do with scalars and vectors, and that's because forces are vectors. They have both size and direction, and this will become very important as we learn more. If, for example, forces are going in opposite directions, you don't add the quantities like scalar quantities. Instead, interesting things start to happen. If you're following along in your revision workbook, pause the video now and complete task number 1. Okay, so forces. A force is a push or a pull that acts on an object due to the interaction with another object. Forces are measured in newtons. This is the unit for a force. Can you name any forces? Contact and non-contact forces. Contact forces are those which are caused or are an interaction between 2 objects which are touching each other. Non-contact forces are those which are caused or are an interaction between 2 objects which are not touching each other. Can you split the forces you've already came up with into contact and non-contact forces? Well, if you've managed to do that, congratulations. If not, let's have a look at some of those contact forces. Examples of contact forces include friction, air resistance, tension, and normal contact force. Friction is a result of 2 objects rubbing off one another. It is a resistive force, which means it works to reduce the speed, or force, of the objects which are touching. It also produces heat. So friction, if you get your 2 hands and rub them together, you can see that they start to heat up a little bit. And that's because the friction is resisting the motion of your hands, and it's changing that energy that you're putting into rubbing your hands into heat. Air resistance is similar to friction, but it is between an object and the air. So air resistance is a little bit like friction, except it's between the molecules of something travelling and the air molecules. Tension is a force which acts across an object like a cable. It pulls a material at either one or both sides and tries to stretch it out. So tension, you might have tension in cables if cables are, I don't know, keeping some lights up or something like that. If you have lights which are being held in place by cables, then that cable will have tension because the lights are pulling that cable downwards. Normal contact force is the force between 2 objects which are touching. If you place an object on a table, then the table will exert a force on the object to stop it falling through the table. The object will also exert a force on the table to stop the table consuming the object. So contact forces are when 2 things are touching each other, and the force is because they are touching each other. Normal contact force, tension, air resistance and friction are all examples of contact forces. Imagine you are using a ski on a carpet. You will have to put effort in because there is friction which is stopping you from accelerating forwards. There is more friction on rough objects like a carpet than on snow and ice. So the rougher an object, as a rule of thumb, it generally has more friction. Imagine trying to carry a large box through the air. You will experience air resistance as the box collides with air particles. The larger an object is, the more particles it will come into contact with, slowing it down. This is how parachutes work. The large parachute produces air resistance, which slows the parachute user down as it is a resistive force. So as the parachute collides with air particles, as you can see, a little example here of this piece of paper or whatever it is, as this collides with air particles in the air, it slows it down, and that force is air resistance. Tension is where a force is applied to something like a cable or another object. It is a force which pulls an object like a heavy load pulling a cable on a digger or bulldozer. So if you have a cable between this part of the digger and whatever this is, and this big heavy thing, well, there'll be tension in this wire because the boulder at the end of the cable has weight and it is pulling that wire at both sides. So the wire will be experiencing the force of tension. Normal contact force is the force experienced between two objects when they are touching each other. If you touch an apple, then you are exerting a force onto that apple, and that apple is exerting a force on you. So as well as contact forces, there's non-contact forces. Examples of non-contact forces are gravitational force, electrostatic force, and magnetic force. Gravitational force is the force experienced between two objects and it is a pull. More massive objects, or heavier ones, exert greater forces on each other. Electrostatic force is where charged objects interfere with each other. If you have a positively charged object, it will attract a negatively charged object. And if you have two positively charged objects, then they will repel. And we covered this in our electricity module. Magnetic forces are forces experienced between magnetic objects. North attracts south, and south repels south. So like poles repel, and unlike poles attract. So gravity pulls objects together. Objects which are more massive, though, will experience a greater attraction. It's also true that the closer the objects are together, the force of gravity between them increases. So if you had an apple in the earth pulls on the apple, and the apple also pulls on the earth. But it is only the earth's pull on the apple that you would think about, because the earth is much more massive than the apple, and the attraction that the earth feels towards the apple is completely insignificant. Electrostatic force, well, electrostatic force happens when you rub a balloon on the wall, and then the balloon becomes charged through static electricity. The balloon is now charged, and will attract neutral objects because there is a difference in charge. Opposite charges attract one another, and like charges repel. This also happens between ions of different charges. In chemistry, you learn that positive ions attract negative ones, and that's shown in this little diagram on the right here. If you have a positive ion or a sodium ion, that might be attracted to a negative ion, or this chloride ion. And, of course, there is the magnetic force. Magnetic force is similar to the electrostatic force in that like poles repel each other and opposite poles attract. So for example, two north poles would repel, but the north and the south would attract. So there's forces between the poles of a magnet. We call force diagrams free body diagrams, and these are just diagrams which show forces. As forces are vectors, these diagrams often have forces shown on them and the direction in which they travel, and that's because forces are vector quantities. Here's an example of a free body diagram. The book on this table has weight, or gravity, acting downwards, and here we've labelled that W. It also has normal contact force acting upwards to stop the book falling through the table. These forces are balanced. Balanced means they have the same magnitude, or they're the same amount. So weight is the same as the normal contact force. And because these are vectors, you can illustrate that with the length of the arrow. So the length of the weight arrow is the same as the length of the normal contact force arrow. if the length of the normal contact force arrow was larger, it would mean the normal contact force was larger. And that would mean the book would accelerate upwards. But we know that this isn't true. If the book is balanced on the table, then those forces are the same. This 10 kilogram mass has an applied force pulling it to the right. It also has friction resisting it. It also has gravity and a normal force to stop the mass falling through the floor. So here, this 10 kilogram mass has an applied force, or someone may be pulling this to the right. Because someone's pulling that to the right and it's touching the floor, you have the frictional force, which opposes that force being applied to it, pointing to the left. And as well as this, you have the normal force, the normal contact force from the ground, and the force of gravity pulling it downwards, because this gravity is what objects feel when they're on Earth and when they're also near other big planets and things like that. So if you're following along in your revision workbook, complete task number 2 and pause the video now. Moving on. Gravity. Gravity is a force which acts towards the centre of massive objects. But everything has gravity, even an apple. But because the apple is so light, the amount of gravity it has is insignificant, and you can just ignore it. When objects are in a gravitational field, i.e. the place around an object where gravity acts, it experiences a force, and this force is weight. Gravitational field strength is what causes objects to have weight. It is measured in newtons per kilogram, which is given the symbol N/kg. The gravitational field strength around Earth is 9.8 newtons per kilogram, but you don't actually need to know that as it's given to you in the exam. So gravity acts on everything around Earth. For the exam, you can assume it's 9.8 newtons per kilogram, and for heavier planets, the force of gravity is actually bigger. And even objects as simple as an apple will have its own gravity, but because apples are so light, you just ignore the effects of the gravity of that apple. So mass and weight are not the same thing, and this is something that's quite important. Mass is simply how much matter there is. So mass is basically how much atoms there are inside of something, how much stuff there is. And this affects the heaviness of that object. It's a scalar quantity and it has no direction. But the weight is different because weight is a force which a mass experiences under gravity. Because weight's a force, it's a vector and it acts towards the centre of Earth. So let's just explain that. Well, this elephant here is 5,000 kilograms. So on Earth, this elephant is 5,000 kilograms. And in space, it's also 5,000 kilograms. However, on Earth, this elephant weighs 49,000 newtons. And in space, where there's virtually no gravity, it weighs 0 newtons. And there will be no force. That leads us on to our next equation, and that is that weight is equal to mass times gravitational field strength. The first equation that you must know for forces is W equals mg. Weight is mass times gravitational field strength. Let's do a little worked example. Jack's mass is 70 kilograms. What is his weight on Earth? Well, we know that W is equal to mg, and we know that the mass of Jack is 70 kilograms. So it's the weight of Jack, or Jack's weight, is 70 multiplied by the gravitational field strength. Well, gravitational field strength on Earth is 9.8 newtons per kilogram. So Jack's weight is 70 multiplied by 9.8. So his weight is 686. The units for weight are newtons, as it is a force, so our final answer is 686 newtons. So Jack's weight on Earth is 686 newtons. Jack now travels to the moon. He must be very lucky. The gravitational field strength on the moon is 1.6 newtons per kilogram. His mass is 70 kilograms. Okay, so what is his weight on the moon? Well, W is equal to mg from the last question and from the equation that we've just learned. So W is equal to 70 multiplied by gravitational field strength. So gravitational field strength on the moon is 1.6 newtons per kilogram. So 70 multiplied by 1.6, well, that's 112. The units for weight are newtons, as it is a force, so our final answer is 112 newtons. So his weight on the moon is 112 newtons, which is much less than 686 newtons, which is what it was on Earth. So we're going to have a little look at the centre of mass now. So this can be a little bit complicated, but just bear with it, and it should come with time. All object masses can be assumed to come from one central point within that object. For example, a car will have a centre of mass where you can assume all of the mass is situated. So because cars have mass because the mass inside of a car is sort of distributed in a way which is uneven, there'll be parts of the car which are heavier than other parts. It's quite difficult to take an average of those masses and come up with a point where you can assume where the centre of mass is. But what you can do is you can take an average of all that mass, and you can say, right, well, we can assume that the centre of mass, all of that mass, is from this point. The centre of mass is where scientists say the force of weight is centred on. So the centre of mass in this car, for example, will be here, and the weight that this car experiences, we say, comes from the centre of mass. Weight and mass are directly proportional, so can you remember what this means? Well, if weight is directly proportional to mass, we say W, and then we'll have this little fish symbol here, and then M, and that means that weight is proportional to mass. So if weight is proportional to mass, it means that weight is equal to mass times some constant. When one is multiplied by a factor, like 3, then the other is also multiplied by that factor. So if the mass doubles, the weight will double, as they're linked by a constant, gravity. So if you double the mass of something, then the weight that that object experiences will also double. If you triple the mass of something, the weight that that object experiences will also triple. So when you have this proportional to symbol, well, that just means this. It means W is equal to some constant multiplied by whatever's on the right hand side. So where K is a constant, we know that K is equal to G. It's gravity, it's the gravitational field strength on Earth in this case. So weight is measured like any other force. We use something called a Newton meter. This device uses springs and tells you the force experienced by an object. You simply hook the object onto the end, and it will tell you the force being exerted on the object, and of course the Newton meter. So this shows a picture of a Newton meter, and what you do is you attach your object to this hook, and it will pull this this thing down the Newton meter, and wherever the level is, well, that's how many newtons of force there is on the end. So you can read off a Newton meter the force which an object is pulling, or the weight of an object essentially. We're going to watch a little video now.
Hello there. We're going to be talking about gravity and weight. Gravity is a non-contact force. All objects experience it, and it is an attraction between objects. Large objects like the Earth and the Moon have noticeable levels of gravity. Something like an apple will have a gravitational attraction, but because it is so small, we do not consider it. Gravity, because it is a force, has both magnitude and direction. Therefore, it is a vector quantity. More massive objects have greater gravity. For example, the Earth has a larger gravitational field strength than the Moon. Gravitational field strength describes how large gravity is. It is given units of newtons per kilogram. Objects have mass. Mass describes how much matter there is in something. Something with a large mass is made up of more atoms and therefore is more massive. Objects will have the same mass no matter where they are. If an object is on Earth, it will have the same mass as if it was on the Moon, or in the middle of space. This sack of potatoes is 15 kilograms. It will be 15 kilograms on Earth. It will be 15 kilograms on the Moon, and in space it will also be 15 kilograms. Weight is the product of gravitational field strength and mass. Here is the equation for weight. Weight is mass times gravitational field strength. weight can be compared to how heavy something feels, and weight is a force. As weight is a force, we give it the units of newtons. The gravitational field strength on Earth is 9.8 newtons per kilogram. Please note that you will not need to remember this value, as it will be given to you in the exam. If we place this sack of potatoes on Earth, we will get a weight of 147 newtons. Obviously, our weight changes depending on where the object is. If the object was on a planet where the gravitational field strength is 24.7 newtons per kilogram, like Jupiter, we would get a different weight. Weight is the mass times the gravitational field strength. So the weight on Jupiter would be 370.5 newtons. This means our sack of potatoes would feel heavier on Jupiter, as our force, weight, is larger. It is important to note that gravity, and therefore weight, always points towards the centre of the body with mass. Therefore, on Earth, our vector quantity weight always points downwards towards the centre.
So that shows the difference between weight and mass, which is quite important because that's probably something that would come up in an exam. I can imagine that being an exam question, something along the lines of what is the difference between mass and weight. And you've just got to remember that weight is mass multiplied by the gravitational field strength, and weight is a force, whereas mass is just the amount of matter in something, the amount of atoms, or how massive an object is. So if you're following along in your revision workbook, pause the video now and complete task number 3. Next, we're going to have a look at resultant forces. So often you get a little more complicated situations where there are multiple forces all acting together. Forces which are all acting together can be cancelled out, and you've got something called a resultant force. The resultant force is where you replace all of the forces and only have one left. For forces acting in opposite directions, simply subtract the smaller one from the larger one. Let's have a look at an example. What is the resultant force here? Well, we have 500 newtons to the right and 300 newtons to the left. So 500 take away 300, well, that leaves 200 newtons to the right. What is the resultant force here? So this bus has 3,000 newtons pulling to the left and 1,800 newtons pulling to the right. So we take 3,000 newtons, subtract 1,800 newtons, and we get that we have a resultant force of 1,200 newtons to the left. What is the resultant force here? So we'll have a 30 newton force acting upwards on this book and a 30 newton force acting downwards on this book. So the resultant force is 0 newtons. Now, I'm going to introduce a new word. If there is no forces in total, we say that an object is in equilibrium. So you could say that this force, despite having lots of forces acting on it, is in equilibrium. And that's because the total force, or the resultant force, is 0. So something with no overall force is in equilibrium. So what's happening here? Well, you can see that this magnet with a north pole here and this magnet with a south pole here are attracted to each other with 30 newtons each. So what would actually happen here? Well, the north pole and the south pole would attract and move together. What is the resultant force here? So here we'll have 400 newtons going up, 400 newtons going down. We'll have 120 newtons to the left and 180 newtons to the right. Well, the resultant force is 60 newtons to the right, and that's because this top force and this bottom force cancel each other out, and the force to the right minus the force on the left is 60 newtons. So the resultant force is 60 newtons to the right. So this log has 450 newtons acting downwards, 400 newtons acting upwards, 100 to the left and 100 to the right. So the resultant force here would be 50 newtons downwards. And that's because 450 take away 400 is 50 newtons. And the 100 to the right and 100 to the left cancel each other out to have an overall force of 0. So we are left with a 50 Newton force in the downwards direction. If you're following along in your revision workbook, pause the video now and complete task number 4. So, it's all well and good just having forces which act to the right and to the left, up and down, but in more cases than not, forces will not be acting in parallel with each other or at right angles. In these cases, you need to know how to find the resultant force. This sounds very hard because we're introducing angles, but it really is much simpler than what it sounds. So, let's have a look at this case. What is the resultant force here? We'll have a tennis ball with an 18 Newton force to the right and a 14 Newton force that direction, 25 degrees from the horizontal direction. Here we have a tennis ball with a horizontal force of 18 newtons and a 14 Newton force acting at a diagonal. The angle between the 14 Newton force and the horizontal is 25 degrees. To find the resultant here, we must construct something called a vector diagram. This is where multiple vectors, in this case forces, are drawn on top of each other to find the resultant. To find the resultant, we must draw out these forces, but it must be to scale. To do this, we need to come up with our own scale. Let's use that 1 centimetre is equal to 2 newtons. Firstly, we're going to draw the first line. So starting from the 0 point here, we know that 1 centimetre is 2 newtons. So if we have an 18 Newton force, that means the line has to be 9 centimetres long, because 18 divided by 2 is 9. So our first line is going to be 9 centimetres long. And we know that this was to the right, because our first force, 18 newtons, is to the right. Next, we're going to get a protractor and we're going to measure the angle, and the angle here is 25 degrees. So draw in the angle of 25 degrees using a protractor. And finally, we're going to draw our 14 Newton line. And of course, that's going to be 7 centimetres in length, because we know that 2 newtons is represented by 1 centimetre. Okay, so that's all of our line drawing done now, but how do we actually find the total resultant force? Well, once you've done it, you need to connect the once you've done this, you need to connect the ends of the lines up with a ruler, as shown in red. Using your scale, measure the line which you've constructed. This will be the resultant force. The line is 15 centimetres long. Our scale is 1 centimetre is equal to 2 newtons. So 15 centimetres is equal to 30 newtons. That means the red line represents 30 newtons. So 30 newtons is our resultant force. So what's the resultant force in this case? Well, here we'll have a basketball with 2 forces acting on it. We'll have a 30 Newton force and a 12 Newton force. The angle between these forces is 130 newtons. To find the resultant here, we must construct a vector diagram again. This is where multiple vectors, in this case forces, are drawn on top of each other to find the resultant. So, we're going to do the same as what we done last time. The first thing we need to do is come up with a scale. So in this case, because we'll have slightly larger values for our forces, let's use a scale which can get more force into a smaller line. So let's use 1 centimetre is equal to 3 newtons. First, draw out the line. So our scale is that 1 centimetre is equal to 3 newtons. So 30 newtons, well, that's 10 centimetres. The direction of the line doesn't matter, so it's good to just do one of them horizontally. Use a protractor to measure an angle of 130 degrees, because that was the angle between the forces. And next, draw in our 12 Newton line. This will be 4 centimetres in length, because 12 divided by 3 is 4. Once you've done this, you need to connect the ends of the lines up with a ruler, as shown in red. And once you've done this, you need to measure the line. So once you've measured the line, that'll be your resultant force. And in this case, the line is 12 centimetres long. Our scale is 1 centimetre is equal to 3 newtons. So 12 centimetres, well, that's the same as 36 newtons. So our resultant force here is 36 newtons. If you're following along in your revision workbook, pause the video now and complete task number 5.
Thank you very much for watching. Workbooks and test papers which integrate with these videos, and online courses are available at our website, backroadtutoring.com.